refers to any y in the category. Теперь на тех трех.
Вот на этих двух только.
Там эти двух.
Ну, и кто-то может передвигать тут, вот когда доски будут меняться. Две вылезают.
Давайте попробуем.
Тут кто-нибудь согласен передвигать?
Если этого не сделать материально ответственным лицом.
Okay. So of course notice that if you know that this f is the right adjoint, then this condition is trivially satisfied. Right? You just move this f to the second argument with notation g, and this will be just g of y will be the representative object of the function. So in the other directions, the trivial observation, the statement is that it is sufficient to have this. Well, let me introduce some notation. So let's go after O star the following function from the category D to the category of functors from the C to this S. So all contravariant functors from C to the sets. So that's a function which is defined. Well, I'm going to write one of the object, so on the object y. So y is some object in D. You just say that this is by definition. You compute the offset of your y f the function, and then they will only do it. Of course, this is just a composition of functors, so it's clear that this is defined also on functors. Okay. So if well, okay, so let's say f admits right adjoint. This is one situation. We also want to together work with this for all part, and I want to say that this thing is representable. Right, so that's exactly the same functor or.
I have a question. Like, why do we write f and the squares like something there? Like, shouldn't we like fix some object in the C? No.
No.
Like, but what does this set then? Like D.
This is all functors. It's under the notation for the
No,
functors.
this I understand. I don't understand what do we mean when we write like D and then we assume a set of morphisms where the first term is not fixed.
Yeah.
Like, what do we mean? We mean the union of all these sets?
No. We mean the following. You take an object y here, right?
Okay.
When you fix a y, this formula give you a functor. This is still a functor here. This is the input of the functor. And this is a functor from C to the sets and contravariant, of course. Because the form is contravariant in the first range.
Maybe it will be a little bit more clear if you remind us how this particular functor, which is the object corresponding to y, works. So what is this?
So if you want to understand this functor, for example, was it
just as a reminder.
you just plug in x here. I thought that this is completely trivial.
Yeah, it is, but just to make it a little bit more.
Right? So without that, this is just a functor. We want to compute this functor on x, and image of this functor sits inside the representable functors.
Sorry, or T?
Or dagger. And dagger is this condition that this is representable. So this whole line is the condition dagger, including this little part.
What does representable means?
It means that this is one of the main factors. So
It's natural isomorphic.
yeah, so here, for example, so you want the definition of representable. So in this case, representable is just well, we want to say something for some object. This is a representable functor, and isomorphic this functor is also called representable. Of course, here it is satisfied because if I know this admits the right adjoint, I move this here, and the g of y will be exactly t representing functor. So the image of this functor is in the subcategory of all representable functors. So I have a category C. Here I have the unit embedding. So there is a unique isomorphism functor G0. So essentially that's the end of it.
What is H?
H is the unit embedding. It's a, okay, maybe I can write a little bit here.
Did they use some kind of dilemma here?
No, I have this functor G0. I know that this functor G0 is unique, right? So if I just say that F lower star is equal to the composition of the unit embedding composition with G0, this exactly means that you have something Y is isomorphic with C something G0. Right? That's the same thing. So G0 is the right adjoint. And if you know that for F and me some right adjoint G is necessarily isomorphic to the G0.
Can you repeat once again what have already happened just from the very beginning?
Well, I introduced this notation for the functor.
Yes.
So this gives me a functor like this.
Okay.
Now, if I assume one of the two conditions, that F is admit the right adjoint, G, or condition dagger is satisfied from the more over part, then I can see from this condition it follows that the image of this F lower star is in this subcategory of representative functors. Because for dagger this is just given, and for if I have a right adjoint, I just use the definition and move this F to the G, and G of Y will be the representative object for the functor. And then I just use the lemma that we put when we discussed the equivalence of categories. Whenever we have a situation, we have a category, another category, and a functor, such that the image is in some subcategory, and there is unique isomorphism functor, such that there is a factorization. So that's the proof. Because
So isomorphism there means the natural isomorphism, right?
isomorphism there.
The unique is unique up to the unique isomorphism means like isomorphism of
Up to,
functors.
yeah, up to unique,
Natural.
not natural isomorphism of functors. Natural isomorphism functors.
How does it actually prove the proposition like this commutative diagram that we did?
So this commutative diagram is this formula,
Yes.
and this is this formula.
Yeah, sure.
This is the same thing
Are they the same?
by definition of the function of this functor and the composition of functors. So I take an object, I compute G0 on this object, and then compute it.
Yeah, that's true.
Well, there, of course, there is a little caveat here. If I have this formula, of course, it's clear that this bijection is natural in the first argument, but it requires a little argument that is also natural in the second argument. Why? But we've constructed everything factorially, so this is kind of factorially depends on y. So it's always immediately clear that it's also natural with the second argument. Okay, of course, this is not a unique proof, or we can use, for example, another proof in Unet's lemma, but essentially, this I think is the shortest possible proof, because when you're writing Unet's, you really need to check that answer is natural in the first argument and the second argument. So more work to do. Okay. So the plan for the rest of the lecture is to give a short characterization of the adjoint functors. So we already know two. So we have this natural bijection, and we have unit characterization. So today we're going to get one more characterization. This will be in terms of the universal arrows. And to introduce universal arrows, I need first to introduce notion of the universal object. So which is quite easy to define. So let's say I have a condition with several parts. So an object say S in some category C is called initial if for any other object X in this category there is unique map. Well, maybe let's say F in the C as X. So from the initial object, there is only one map to any other object. And we have a dual definition. So an object, say T.
Including the object itself, right? So
Yeah, so if you take, for example, X to be S, so this unique map is just added to this. So an object T is called terminal. If you have a dual condition, so for any X in the category, and there is unique map in the other direction. So there is unique map. So I guess I can also reformulate this condition differently. So this is from the terminal, so this is dual. So I guess I can also say that just cardinality of this set for any object is equal to 1. That's the same, right? And of course, I can do this for the second part. Okay, 3. An object which is initial and terminal is called zero object. And since we have a zero object, so let's call this object Z. We can introduce the notion of the zero map. So if you take two objects, map this to the zero object, and then from the zero object, then this map is called the zero map.
doesn't it mean that zero object is isomorphic to all objects?
No, this map is isomorphic.
Yes, but if there exists only one, then the composition will be like that isomorphism, right?
What composition?
Okay, let's see.
This is
C
this composition. This is zero map.
No, I mean from. Okay, what's the
For example, if we take abelian groups, if X and Y are two abelian groups, this can be a beta zero map that sends everything to the zero.
No, wait, I mean, we have the unique morphism from Z to Y, let's say, and the unique morphism from Y to Z. So if we compose them, we get the identity map of Z, no?
If you compose them in the other direction, not like this, but you just that's
Yeah. Oh, it doesn't mean that's isomorphism. Yeah.
So in this one, this is just a zero map. Okay. So little theorem, which is easier to show but still important. So a universal object or universal object is a terminal object or initial object. So initial or terminal object is unique up to unique actual objects. Of course, it's enough to prove this for, say, initial object for the terminal for which is 2. So let's take S and S prime, the 2 initial objects.
Sorry. So you said that a universal object is just an initial or a terminal object?
Yeah, this is just a name for this kind of objects. Initial objects or terminal objects, they call universal objects.
Are there any other universal objects?
Not really. So essentially what we're going to do, say in February, we're going to start this category, construct a new category, a little bit larger, and then find the initial or terminal objects in this new category, and this will be something interesting from the point of view of the original category.
Okay.
So essentially what you have in the category is the initial and terminal objects, and then it can be used to this kind of objects.
Great.
Yeah, so but let's finish with simple observation. Suppose I have 2 initial objects. Well, correct, it means that since x is initial and I can take x to be at s prime, there is a map like this. Say, let's call this F. And of course, since s prime is initial, there is a map in the other direction. Right? Now, let's take a composition F and G. So what's the composition of F and G? So if we go like this, it will be map from S to S. But there's only one such map, the identity of S. And of course, the other composition by the same argument is the identity of the S prime. So they are isomorphic by the maps F and G. And of course, we can see that these maps are uniquely determined because this is the initial object. There's only one F, there's only one G. Okay, really trivial observation. Now, let's look at several examples. So let's start with the sets. So, do you see what's the initial and terminal object in this case?
0 set must be 1.
What's the 0 set?
Empty set.
And a set with the only object is defined the terminal.
Yeah.
Yeah, true.
So here you can notice that the initial object is just unique. There are no isomorphic objects. But the terminal objects, though, you have plenty of terminal objects, they all isomorphic. And the isomorphism is indeed unique because though you have 2 points, there is only one vector sending one point to another point. Okay? Now what if I go to the topological spaces?
Once again, the same.
Yeah, so the answer is the same. And for example, if I go, well, if I want, I can go to the metric spaces, and the answer is still the same. So in these examples,
Okay, metric spaces and what are the morphisms there?
well, I think you can take any morphisms in this.
So it doesn't matter, right?
Yeah.
Okay.
Okay. What if I take category of monoids, where they have an initial terminal object?
A monoid consisting of a signal L. It should be at least something of this.
But this monoid is not only one element, the identity.
Yeah.
Is this initial or terminal?
Yeah, it must be. It must be both.
Yeah.
At least in groups.
Because identity can only go to identity, right?
Yes.
And like, if there is only one map inside, 2 is and like from it. So it's 0.
So in this case, we have 0. Of course, for groups, the same works. category of R modules.
0, 1,
Yeah. So again, Z is equal to the 0. So notice that abelian groups of vector spaces are special cases. So all these categories, zero object which is 0 as module. Okay, rings.
But rings are no zero.
Integers is
Ah, we have to
integers are the initial.
Do you agree with this? If you have integers, then definitely you have only one map. This, well, we assume that the ring maps 1 to 1, so identity to identity. And if you know where identity is going, you know where any integer is going. Like you just go to the integer type identity. So that's the initial object. And what about the terminal object?
The zero ring, if we treat it as a part of this category.
Yeah. So here this depends a little bit on the definition of the category. If you have a zero ring, then this is a terminal object. But if you don't have a zero ring, well, then there is no terminal object.
It depends on if the ring is Artinian or
No,
It depends.
Artinian. I mean,
It depends on whether you want to consider this as an object in your category.
sorry.
Because rings
Zero.
we like
Why zero is not
0 and
equal?
1 not to be equal, for example, and sometimes we take it as a as something which should be there.
So if you don't consider unital rings, right, we can just say that 0 ring is there. Because like the only problem is having like 1.
So that's the answer. Well, if you want to consider rings without 1, then you can use this as an initial object, just 0 goes to 0. But if you insist that all your rings have 1, right, then this doesn't work. Because well, you're supposed to get 1 is mapped to 1, and this is not true for this ring.
But in both cases, Z is also a function.
Yes.
But we are not.
No, if you don't have 1, now Z is an issue.
Oh,
How do you define that?
Yeah, so the rings that have 1 and don't have 1 must be in the different categories, races, or what?
So what?
Yeah, of course, because we need to have 1 somewhere.
Okay, so maybe one more example. I can put it here, so 5. So let's take P to be a partially ordered set, so PO set. And consider this as a category. So what is initial terminal objects?
What is people?
Partially ordered set, 2.
Well, when we have like the whole set of only 1 object.
Minimum and maximum are
it's not kind of everything.
Oh yeah, actually.
No, the category is P itself. It's not a category of all sets.
That's the minimum.
Okay. So then, so S is the smallest, and P is the largest or greatest.
What are objects in this category?
elements of the school set.
Yeah.
Elements of.
All
Ah,
set.
all fixed.
Yeah, so P is fixed, and we consider this as a category. So maybe
But actually,
P is a post set, and then we consider the category P underline.
isn't something broken there? Because like there can be like many largest elements, or
No.
no?
Well, by definition, the largest element is unique. Well, this is because we have, if you go back to the poster, it means that you have this inequality, and this is for AX in the offset.
Ah,
So of course we can have a situation like this.
okay. Yeah.
So, for example, this is the arrows. Then you have two minimal elements and two maximal elements, but there are no initial or terminal objects.
Yeah, that's what I was asking.
And so with this example, we can immediately see a lot of examples without any initial or terminal objects. Okay, so next notion that we need is the comma category. So suppose you have the following situation. You have three categories, C, E, and D, and two functors, F and G. So we're going to write them like a diagram. So then we have the so-called comma category. Comma category that depends on these three categories and two functors. Notation is this. So that's the comma category. The notation is with the downward arrow.
What is it in Russian?
Yeah. Well, there is notation categories but probably this is not the best translation. So even in Russian, I think people say comma category. Comma category. Okay, so what are the objects? Objects are triples. So C, H, and D. So where C is an object in the category C, D is an object in the category D, and H is a map. So H is a map. When you apply to the object C, function F, no? And then you apply to the D function G, you get two objects in the category E. And here you can take a map H. So maps. So what I want to define a map of the C, H, and D to another triple C prime, H prime, and D prime. Well, this
It's a pair of morphisms in categories which yield.
yeah. So we need a map from C to C prime, right? And we need a map from D to D prime. Or let's give them some names, maybe F and G, right? So these are pairs of two maps, such that if you consider the square, then the square is commutative. So you can apply F to the C and to the map on C prime. Here you get some H, which is a map to the G of D. Here H prime, G of D prime, and here is the G applied to the second map. So this has to be commutative diagram. Okay, that's a very general definition, but you mostly will be interested in special cases. Now, for example, you can take an object C in the category C and in the following situation. So the first functor F is just the identity functor of the category C. And the second functor is from the category 1 to the category C. So this is the category, is only one object, only one map. So this map is completely determined by an object. Let me call this functor C lower star. And so 1 is the C lower star, sends 1, or maybe I don't know, star, we use this notation before this. This one?
No.
No. This is a very trivial situation. This is just an identity function, this is just a function.
Yeah, okay.
By
No
no
problem. Yes.
So it's not representable.
Yes,
Quite
yes.
simple. Okay? So in this case, if we'll say this is first special case, this is called the slice category. Well, if you just look at the definition that we gave, well, the objects are just pairs X and H, such that, or maybe C and H, such that C, of course, is an object. No, this is why I want to use notation X, because C is already fixed. So this is X and H, so X is an object of the category C, and H is a map from X to C. This is the data.
X is subset.
No, it's an object. Oh, the triple has two objects and the map, right? But here you can choose only one object. And if you apply this functor, the second functor, which you call G in general definition, well, we always get C. So G of anything is just C. So it's a diagnose like this, and the first one is just identity. And so this is the
Don't we have like
C
only one?
is image of one.
Oh.
We fix an object here, and then define a factor on the category 1, such that the unique object here is mapped to these objects.
So it's the category of C objects in the category C.
Yeah, so this is the category over C.
Okay.
So of course the morphisms in this case, this is just the morphisms such that this triangle is commutative.
I'm a bit confused. Why don't we write like the object, the third object in the B? Because it's like the same.
Because there is no choice for the third object.
Okay.
Right? Because this category has only one object, and when you compute factor G, which is this functor, on this one object, you always get C. It's a constant answer. So there is several notations for this slice category. Of course, following the formal definition, I need to write something like this: 1 over C, comma category with the C over star. But nobody writes this, so people usually use shorter notation. Where instead of the identity factor, you just write the category and then the object.
It's a notation for a slice category.
Yes. And there's even third notation. Since this is objects over C, you can use this notation. Well, I don't want to repeat this, but you can define the cost-slice category. Where essentially you just sit around these two functors. So this will be formally C comma category with a C star 1 over C, which is for shortness usually is written as comma category of C and the category C, and this is the same as the cost-slice category. Okay. And the third example, actually for cost-slice categories, you already know some examples. For example, pointed sets or pointed topological spaces. These are examples of cost-slice category. Because the cost-slice category have objects and they map from some fixed object. So for example, if we take a singleton as a fixed object, then this exactly a distinguished point in the set.
Actually, aren't, for example, our modules all this form in some sense?
Well, you want to say, this is not not in the example 3 that I'm going to present. Let me formulate it as a question. So it looks like you want something like this. You want a category of rings. Right? So here, say you have 1, then you fix the ring. This will be functor used by this one object, and then we consider something like E sub z from the abelian groups, where E sub z of some abelian group M is just by definition endomorphisms in the category of abelian groups. Okay. Right? Looks like you want to consider this thing.
Yes, so.
Then, well, of course, if you just rewrite the definition, it would mean that we have a map from the, in the category of rings, have a map from the R to the endomorphisms. Notice, right? And that's exactly the structure of an R module
Yes.
on the
Yes,
abelian
yes.
group. So unfortunately, this is all false. This is not a function.
Okay.
Well, we can define this on objects, but how are we going to define this on maps?
Yeah, well, I was just trying to make up some less sophisticated example when one from the algebraic geometry, where you have, for example, K schemes for K. What maybe
Yeah, so you can do the dual case. You can consider the costless category, and for example, category of R algebras or some fixed probability for ring R.
Yes, yes. It would work.
So an example for costless category will be something called algebras, when we commutative algebras, or something commutative ring R. And this is not an example because this is not a function. So it looks nice and everything almost okay, except this is not a function. Okay, and I wanted still to present the example, well, not an example, but a special case 3. So here I have also a special case, but a little bit more interesting. I have an object will be a functor from 1 to the C, and the second functor is just any functor in G, no restrictions on G. Again, if you just apply, well, first of all, let me again fix notation, so general notation will be something like this, but nobody writes this. We'll just write one category for the functor C, object C, and functor G. So again, objects are pairs on the D and H, such that of course D is an object in D, and F is a map from the C to the right? If you just look back at the definition that you have in general case, this will be what you have in this special case. Okay, and morphisms.
Sorry, H must be the one there.
Sorry, this is H. This is there. So F will be here. So if I want to introduce a map between two such objects, well, you have one such situation, you have another such situation, you have G and G prime, this is H prime. So what's the map between two diagrams? Of course, this is a map from D to D prime, such that this is commutative. Example. So let's take the following situation. So at 1 in the middle at category of sets.
I'm sorry, didn't we actually check that these things are categories? Wait. I mean,
Introduce the morphisms and objects.
yeah, but shouldn't we check some that morphisms?
Both on the composition.
Yeah, that they are sourced. Yeah.
Well, but it is clear since it is coming from the morphisms in the given category. So for example, here F is a map from D to D prime, the category D. So G is the functor. There's compositions to compositions, so there are no problems here.
This is left to the student as an exercise.
And a simple exercise. Okay, so this is the situation I want to consider. So sets and this is groups. Okay, I want to not just any function g, but I want to choose a specific function, namely the forgetting function. I take a group and forget the structure of the group, just get a set. So of course we can just repeat the definition, but I want to ask you a question: what's the terminal object in this category? So what's the notation? Well, S of a category belongs to you. So S is just a fixed set. Okay, so let's call this terminal object GT and the map HT. So T for terminal. So that means that we have the following. If I have, well, I have S, there is a map HT to the U GT. And whenever I have any other diagram of this form, so any other H to any other of G, there is a unique map here, so let's call this map here. I just repeat the definition of the terminal. Terminal. I don't want terminal, sorry, I want initial. Initial objects in this category, so this is the right direction we have. And of course, it doesn't make sense now to call this T, so let's call this I for initial. Okay, that's the definition of initial object.
We have the only morphism from it to anything.
Well, and this is the. Actually, maybe this is not the best way to write this. So here, this is U of F, and there is unique F, which is a map from the G initial to the G.
Maybe it is, yeah, I guess what we know about U of F, that's a homomorphism of groups after we forgot that it was a homomorphism of groups. And what we know about this homomorphism is that it sends the identity element to the identity element.
Sorry, I don't understand. This is a map of groups. This is just a map of sets.
Yes, but we know that that's not just a map of sets. We know that we have forgotten something, that it sends identity to the identity. And maybe it has something to do with the morphisms which send the set consisting of the only element to the identity in the group.
Well, also notice that you ignore this part of the diagram. You have a fixed set, and the set is mapped to any group. Well, we need to avoid the forgetful function, but naively it just means that there is a map from this set to the group.
Maybe it's something like group free generated by S.
Yeah. So GI is a free group generated by S. If you just look at the definition, this is the definition. So whenever have any other group, you know how you map the set in this group. We can uniquely continue this to the free group. So here, the free group generated by the set S.
Okay.
So this is another point of view on the free object. And this is works generally for any variable joint functors.
So what's the claim there? We claim that every such object HI is.
We claim that in this particular case, if you take this category, we can compute the initial object. So this is a formal definition.
Yeah.
And we can see, since the initial object is unique after unique isomorphism, we see that if you just plug in this to be the free group, this works. by the definition of free group.
Okay.
Right? So because if you have set the set map to some group G, there is a unique way to continue this map as a set map with all XO groups to the group GI, which is a free group generated by S, the given group G.
Yeah, but if GY is just the group that consists only of identity, doesn't the same hold? Like assume GY is just an identity. Then like every map is like sending identity to
Well,
identity.
we have this fixed set S, so we want to send everything to one element identity.
Yeah, it's fine.
Okay.
Yeah, like but isn't there some kind of contradiction because we said that all initial objects should be isomorphic, and I don't see the isomorphism between, let's say,
If we send everything to identity, then we should send S, H of S to be one element.
yeah.
If HI was a trivial map, then we cannot complete this diagram with QF because any completion would yield H to be equal to the trivial map as well. So it's some kind of the opposite of the answer because our answer should be universal enough, but and our situation that HI is trivial gives us literally no opportunity to do anything non-trivial.
Yes. So, anyway, so,
So it should work for every H right there, or what?
of course, so this is initial object, so it means that whenever I have a map like this,
Yeah, and so if we take that identity map, then it just doesn't work for every H.
so this is not committed to that. So what we see in this example that we can actually characterize the adjoint functor to this functor as as some data related to the initial objects in the comma category. And this can be done in general for any adjoint pair. So this is what we now going to show. Before we show this, I have a little formal definition. So definition, a universal arrow. So H. So where this is a map. So again, I assume that the functor G and object C is fixed, and I want to find universal arrow. So this is arrow like this, which is initial object in the category we just defined. This is just an emoji, nothing really.
Universal what?
Arrow. So meaning this is H and also meaning T. So this is universal in some sense for any object C with respect to the function G.
And G is the functor from what to what?
Well, this is the situation that I just raised here that was in the third example.
Okay, so it's from D to C.
Okay. The slice category of C2 itself.
No, this is not a slice category. The slice category we fix an object and the other functor is just the identity. Here we have a non-trivial functor G.
Yeah, is initial object in which? Isn't it a slice category? Of
This is slice category for the C and G.
G. Okay, thank you. That's clear.
Okay. So lemma, if functor F from C to D, sorry, if functors F and G, so I mean the group where F and G are adjoint, then the pair F of C, theta C, is a universal arrow, meaning just a general object, or sorry, initial object in the comma category. So in the C, G, and that is true for any object C in the category C. So from the adjoint pair, we can construct a universal arrow always. Okay, so let's take pair D and H, which is just an object in the comma category.
C and D are categories. We have C, arrow, G.
C is an object. This is not underlined. So this is the category that we consider for the first fixed object, which is induced amount of this category 1 and this category. So for this, you want to apply comma categories to the adjoint functors. And to do this, it's not to consider only such special cases where we can make comma categories. So the first functor is just functor induced by the object. So I want to take an object in the comma category. So well, what it means in terms of the more naive data, it means that I have an object, right, and I also have a map H, which let me write it like this. This lives in the C object C, and the G applied to the object D. Right? But then by the adjunction, I know that there is H bar, which is, and this is unique, so this is a bijection, so there is a unique H bar that lives in the D underline F of C D. Okay, now I have this diagram. I have C mapped by the eta sub C to the G F of C. This is the unit of the adjunction. And I want to show that this is an initial object. Well, suppose I have any other object, H, so I start with some object, D and H, and I want to construct a map here. Sorry, this is not D, this is G of D. And I want to write G of something. Well, first, this is just H bar. Okay, think about this. Is this clear? So I want to show that this diagram is an initial object. For this, I choose any other object in this category, which is the diagram, which is this part. But if I look at this diagram, H lives in this home space. And I have an adjunction, so it means that I can take this G and move it to the first argument. So there is an H bar moving in this space by the adjunction. So I just add this H bar is unique by the adjunction. So I'm claiming that if I just plug in G of H bar here, I get a triangle, and that was
First property of natural naturality of that.
I would say that this triangle equality. Equal.
Well, yes.
Well, I think even better, I think we can say that this is a definition. We gave a definition in the proof of the theorem of what is H bar, if you know this and this. Right? So that's this definition. So anyway, that was something that we wrote in the seminar. That's not a problem. That this triangle was figured. Okay. And the main theorem. So suppose that before we have two functors. So there is one-to-one correspondence between the following data. So first, adjunction, and second part, natural transformation eta from the identity functor to the position G and F, such that if you consider pair F of C eta sub C as an object in the comma category, so this is universal arrow for any C which is first. So if you have a data in A, we already know that we can produce data in B. We just check this in the lemma. So this is done. In the previous lemma. So as in the last time, we need to go from data in B to the data in A. So reconstruct a junction. Okay, let's do this. Let's take any object D in the category D. And then for this object, set epsilon D to be a map from the fg of D to the D. Map? Well, we know that this is a universal arrow, meaning that this is an initial object. So I can apply this when C is equal to the G of D. So then from the pair f G of D, eta sub G of D, there is a unique map to any object. Well, for example, let's take D and 1D.
So, what is written in the theorem? There is one correspondence from A to B.
Yes, between data in A and data in B.
What do we mean by data?
Well, here the data is just an adjunction.
Let's
Why,
actually.
right?
Well, that's won't be convenient for this particular theorem. So we're going to take that we have unit and k-unit, and they satisfy triangle identities.
Okay,
So
so
this
the
is
set of maps like for units.
Yeah. So two natural transformations. Eta is like this, epsilon is like this, satisfying triangle inequalities. And in the B we have what's written. We have a natural transformation eta, such that for this eta, if I kind of compute this on the object C, I get the universal arrow, and that is true for any object C.
And what does this bottom line mean? What does this bottom line mean? Is it a desire or is it a definition? And if it is a definition, how does it work?
Well,
How do we set this epsilon D?
so I'm saying that I can choose this or set epsilon D back on this by using.
Oh, okay. So it's just the introduction to what is happening here.
So by notice, so by using, if I use object C, which is G of D, then for any C, this is true particular for the of this one G of D. This is true. This is initial object. So there is a unique map to this.
Okay.
To this thing. And if you want a diagram, so this is how the diagram would look like. So we have eta G of D from the G of D to the G F G of D. So that's an initial object. Here I have one G of D, and then by the fact that this is a universal object, there is a map, unique map epsilon sub D with this, right? That if I write G of the epsilon sub D, then this is given to limitative triangle. So the existence of this epsilon D follows by the fact that this is initial object.
Okay.
For the G of D. Notice that this is one of the triangle identities for the natural transformation eta and epsilon. So essentially by construction, we already get one of the triangle identities. But we still have a lot of things to prove. So this is just a map. For any fixed object T, we get a map. So first of all, we need to check this natural transformation. So naturality. epsilon. So this is our next step. So suppose I have a map Q from D to the D prime. Well, to prove neutrality, actually, I need a lot of space. So I need to erase this statement of the theorem. I have only two backwards.
How would we get epsilon D?
Well, this is the initial object. So it means that for any diagram like this, there is a map epsilon D, well, exactly like this. If you just go for the definition of let's say, comma category and initial objects exactly, this is a map of this form, such that if I apply G to this map, I'll get the vector diagram, and this map is unique.
Yeah, I'm sorry, shouldn't there be like G of D, like that, first one is T, comma, 1 over D. 1. And is it an identity map in the category D and an object D or what?
Here?
No, I mean after. Yeah, a bit right. Yeah.
This is identity on the object. This is not underlined.
Shouldn't it?
What's written here is two objects in the category, in the comma category, and the morphism exists just because of the initiality of the object on the left-hand side.
Yeah, that's fine. Shouldn't we have like one object and one morphism? I mean, the other object, I guess, is clear, but why do we have such morphism? Or do we just take like that?
We just take this pair, we take object T with the map which is identity.
Okay.
So if you remember that the general is supposed to C, H, and the map to the
Yes.
G of T. So now I'm just choosing this to be G of T.
Okay.
Right? And then H is just all identity.
But identity of D or G of D? Like I don't.
Oh, the same thing. I can write G of D. That's what I really have here. Yes. Makes more sense if I write G of T. Okay. To prove the neutrality of epsilon, I need to look at the two commutative diagrams. So first, commutative diagram is something that we already obtained before. So I'm just kind of rotating the triangle that we already know. Flat triangle. So,
What's this map? U, G.
well, this is eta sub G of T. Well, you can always read the index of this map because the index of this map is the same as the object. So now, then I have some, well, I choose this map Q. So this gives me a map from the So the upper triangle we already know, and this triangle is just composition with the G of Q. So trivially we get this diagram.
What's
So
the middle arrow identity?
what middle arrow of this?
Yeah.
Yeah, this is the same one that you have. Now let's look at the second diagram. So where I start with the condition that the eta is natural transformation. This natural transformation for the map Q. add the same diagram, the same triangle as before, with the epsilon sub d. Okay. Natural transformation for a triangle as before. Yes. Now, this thing is an initial object in the common category, which is the same thing as this thing. Right? So here, the map is the same. This is still one. Namely, the map is G of Q. Here, G of Q, and here this is still G of Q. So it means, since from the initial object to any object there is unique map, this map is the same as this map. Hence, we get the following. Composition of the Q is epsilon sub d, is epsilon d prime, position is f g of d. Okay? So by looking at these two diagrams, we can conclude that epsilon is natural. But this is exactly the condition of naturality. But written not in terms of diagrams, but in terms of equations.
So we just checked whether the polymorphism is worked, and that's why it's natural.
Yeah. So if you just present this identity as a diagram, you can get the definition of neutrality.
Okay.
So because I have a lot of diagrams, I guess I need to erase again. So now I gave you a definition of the epsilon. I checked one of the triangle identities. I checked that epsilon is natural. So I guess I need to check that I have the other triangle identity. Second triangle identity. Again, this is the proof is by looking at two diagrams and using to have an initial object. So the first diagram is kind of tautological. Clearly, this is the elliptic triangle. Right?
This is in new topic.
We continue the proof. So so far we introduced the natural, we introduced map epsilon. We checked that this epsilon is actually natural transformation. The one of the triangle identities was almost by definition. And now we want to check that there is a second, the second triangle identity is also true. And to prove this, again, I want to compare two diagrams and to use that initial object. So the first diagram is this tautological diagram. Also notice one important thing. So far, we haven't used that this is an initial object for any C. We only used for the C features of the form GOT, yes. So this is the step where we actually need that this is true for any object C in the category C, not just for the form GOT. Okay, first triangle is clear, and the second triangle is first the natural transformation. Applied to the natural transformation itself. And then, as before, I combine this with the triangle that represents the first triangle. The first triangle identity applied for the objects of D prime. No, this is, well, sorry, I missed the, okay, I'm kind of started with the correct diagram. And then I use the diagram that we used before. Sorry, that's not the right thing to do. So here I have object C, then this will be natural transformation eta G F of C to the G F G Okay.
In the bottom right.
Yes. So I think now this works.
Yeah. Okay.
So this is the map, and this is natural transformation. We want to apply this natural transformation to the map itself, so natural transformation itself. So this is the given map, this is the result of the GF applied to this map, and this is the eta on this object. Okay, this is much better. So here I have G epsilon f of C. So again, applying the first triangle identity, but for object f of C. So the G f C, and this is the identity. Natural transformation and triangle we got before, but for the object f of C. So 1 f of C is epsilon f of C composition with f equal to C. This is what we get.
How did we get the last triangle?
This is the same triangle that it was in the very beginning, right? Where we defined epsilon. But now this is a triangle where D is equal to the f of C.
F is equal to what?
D is f of C.
Ah, okay, yeah.
Again, since this is the initial object, and this is just some object, so here we have initial object, some object, so this map here has to be the same map as this map. So this is this identity. So the last part, I think I'm going to leave as a little exercise. So uniqueness. So here you want to assume that if you have epsilon and epsilon prime, two natural transformations such that eta epsilon and eta epsilon prime both satisfy triangle identities, then epsilon is equal to epsilon prime. And this finishes it.
And should it be an epsilon prime, or it's just one fixed? Oh, okay.
But
It's C underlined. Okay.
So suppose I have two such natural transformations, I was able somehow to construct them, then again, if they satisfy triangle identities, the proof will be more or less the same. You just need to write a couple of diagrams, use the fact that you have an initial object, and conclude that epsilon is equal to epsilon prime. Okay. So we get ourselves a third description of adjoint functors, and this is the last one. So in particular, we can conclude following corollary. So functor G D to C, so this is just one functor, has a left adjoint if and only if for any object C in the category C, the comma category CG as an initial object. Well, as I promised you, all the questions can be reduced to the questions of the initial terminal objects, for example, existence of a left adjoint. And of course, all the story have a dual side. If you want an existence of a right adjoint, you just find the corresponding comma category and ask for a terminal object. You can dualize everything. Or trivially, just applying off to all the objects. Okay, proof. So in one direction, this is already done by the previous theorem. So in another direction, so set f of C eta sub C to be an initial object. So notice at the moment it's just notation. I know that I have an initial object, but I need we have a name for this object, let's call this C, and name for this map, so let's call this eta C. So what we need to check, we need to check this is a functor, and this is a functor, and this is natural transformation. Well, this is not so hard for the second part. Okay, so functor, if I want to define this on the objects, I can do it like this. It is unique after unique isomorphism, so this makes sense. Now, if I want to understand what this functor is doing on the maps, I need to take a map. So if f is a map from C to C prime, then I can set f of f to be a unique map such that I have the following combinatorial diagram. So I have C, eta sub C to the gf of C. So that's a diagram corresponding to this pair, which is an initial object. So then another diagram is the following. So from C, I have a map to C prime. This is map F. Then from C prime, I have another map, eta sub C prime, to the gf of C prime. Right, so this composition will be another element in the comma category, another object in the comma category. Well, from the initial object, there is a unique map. So the unique map is G of F. So in this way, I can define this F acting on maps. Notice if you just deform this diagram back to the canonical commutative square, this means that the eta is a natural transformation. So the only thing that is left is to check that with these definitions, this is for objects and this is for arrows, this gives us a functor. Right? So I need to check one is close to one, position, and that's an exercise. And do the proof, and then of the lecture. Мне лучше начальный нравится.
Где мы тут использовали, что объект начальник?
В смысле, где мы все доказано, но во всех шагах.
Не, ну в этом последнем.
Что такое f на отображении есть маленькое f. Оно вот это вот отображение существует по той причине, что это начальный объект.
То есть для каждого существует стрелка, вот это она и есть, да?
Да, при любой диаграмме здесь должно существовать какое-то отображение, что если уже его применить, то здесь будет коммутативная диаграмма, да? Но вот отображение это вот это.
А дальше это функция типа сами.
Ну, это надо написать определение для определения, давай проверить, что композицию смысл. Это такой некоторый довольно слабый, мало применимый критерий, когда у нас есть сопряженный функтор.
А и сильный хорошо применим.
Есть то, что называется graph soft, general joint functor theorem, special joint functor theorem. Но, на мой взгляд, они тоже не то, что очень удовлетворительны. Они тоже так или иначе сводятся к тому, чтобы как-то перерастать объекты в категорию исполнителя.
Поиск, получается, начальных объектов типа проще, чем строить joint functions, да?
Нет.
Нет? Зачем?
Ну, мораль здесь стоит наоборот такая, что если мы интересуемся какие-то просто абстрактные вопросы теории категорий, само по себе сложные, да, то все вопросы, которые вас интересуют, это вопросы существования начальных конечных объектов. Никаких других вопросов у вас интересовать не должно, потому что все вопросы свойственны так или иначе существованию начальных конечных. Просто категории, которые вы получите, мы категории, которые начинали, там, sense, groups, Это очень простые вещи, там сразу понятно, что они есть, и как они устроены. Но мы должны строить всякие вспомогательные категории, категории специальных видов. И в них уже совершенно не очевидно, что их совершенно нет. То есть сложность понимания существования начального объекта, там такая же сложность понимания существования скаженного фактора, если никакого такого выигрыша нет, кроме морального.
То есть можно так, наверное, перефразировать, что наличие сложных структур в простых категориях можно перевести в отыскание простых определений структур в сложных категориях. Ну, тут вопрос к тому, что, наверное, не все теоретико-категорные вопросы сводятся к тому, чтобы отыскать какого-то специального рода объекты, например, категории sets. Но мы это сводим в итоге к отысканию.
Да, ну да, какой бы вы поставили вопрос, может быть, вопрос существования в основном, конечно, существует что-нибудь, переформулировать, не существует начальный и конечный объект, какой-то вспомогательный может быть. Это как бы был первый шаг в направлении реализации слова. Мы закончим сегодня первую главу, такие вот некие общие слова. Сопряженные очень более содержательно. Вот, а вторая глава предел по пределу. Все предел по пределу это просто инициатор, начальник, конечно, объект, помогает предел. Ничего больше.
Ну да. Он все удивит.
А чем-то пользоваться можно?
Могут быть.
Должно быть первой паре.
Зачем?
Что раньше? Голова лучше работает.
Если мне надо без разницы, можно говорить, да? Можно в следующий раз, на следующий день проголосовать. Кто хочет. Но все равно.
Задачи на квизе будут примерно по сложности сопоставимы с задачами на семинаре. Или они другие совсем невозможно.
Не будут людей похожи, образованности, я не знаю, что это имеет нужно как семинар.
Но, скажем так, на семинаре мы разбираем все-таки больше 3 задач, правда?
Мне кажется, да.
Да. Потому что тут мы можем прописать всего 3 задачи. 4 за
Решал,
4.
что я решал, что
3-4. Все равно больше, чем 4 задачи можешь разбираться.
но семинария коллектива действует, что больше не всегда сказал.
Ну, то есть они будут посылаться реально как задачи на себя.
Я надеюсь, что ничего посложнее еще почему.
Ну, просто если я понимаю, на семинарах мы часто проверяем какие-то просто определения, свойства, все-таки надо видеть, что там какие-то другие типа задачи.
Я обязательно скажу, что конкретную задачу, вот две категории, вот двух, найдите левый и правый сопряженные значит, не существует. Обязательно будет. И там я дал мне какую-нибудь категорию, спрошу, когда что они понятны или нет. А когда что не могут себе понятно. Вполне конкретные такие вопросы, для того, чтобы сделать семинар. Просто преимущество, потому что я могу спрашивать по всей математике. Я могу просто еще например, что одну геометрической геометрии, одну категории, одну плавание.
То есть Пуш предполагает знание всего этого глубоко, да?
Нет, всего этого на поверхности.
Ну,
Тебе просто надо знать какие-то там морфизмы.
часть из того, что там говорилось, я уже забыл. Ну, там по линейному.
Почему мы придумали?
Ну, я не знаю, по алгебре. Ну, короче, что-то там. Я забыл.
Является тензорных произведений.
Да.
Сегодня создался на страшный семинар.
Ну, ладно.
Просто это произведение дает очень хороший пример сопряженных функций. Зачем вы занимаетесь, если вы боитесь нас определенного анализа каких-нибудь цифр? Хотите нам это определить? Как вы считаете, как новый рекурсивный пространство? Просто я забыл рассказать,
Еще есть коэффициенты заменить. Как это логика?
как это понадобится.
Ну, понадобится.
Формулу делают, короче. Да. Тем не менее, там такие простые данные определения, это все должно быть максимальной общности.
Максимальная сложность.
Общности. То есть минимальная сложность.
Вчера уже писал про технические проблемы. Учебно. Поэтому мне ссылали тут. Типа сегодня будет. Сегодня
Я так понимаю, вы играете, что-то сломали.
не знаю, я ничего не ломал, я к ним не приближался.
Что было в ней?
Я вообще не знаю, как раньше все снималось.
Короче, это когда?
Ну вот, неделю, да, 2 назад. А
Там камера была.
ну, видимо, кто-то забрал камеру. Просто вряд ли думаю, что она сломалась. Чего не сломалась?
Да, там есть два набора просто. Треножник, камера, ноутбук, микрофон.
Да.
Все, что надо вначале уже настроить.
Она перестала записывать.
Я не знаю, что случилось.
Я вот знаю, что на группе код у нас постоянно проблема. Камера обязательно последние 30 минут бегает. Когда решает, что там уже какая-то совсем начинается, когда надо выключаться.
Важно раз участь.
Предохранители вылетают.
take category of fields and forget to compare to the set. What's left adjoint to this function? Что значит сосед?
can this program be formulated in terms of initial and terminal objects?
Exactly, but if you by the last parameter you call the existence of the function. I think that's exactly the existence of the initial object in the common category. I don't think this is helpful.
It seems that there is no such a I'm not sure. Maybe I'm wrong. We want a bijection for x is a field, yes?
Maybe this, we'll call this F,
Okay.
free function.
F and S is a set. Yes, and we want a bijection between all maps from f of x to s. Yes.
F of x is supposed to be the left adjoint, right? So this has to be a field. So the map has to be to some field.
Okay. I mean u of f. Yes, u of f is a set, and s to s, and
I mean, this is correct.
no,
Let's just try what we have. So we have fields. We have left adjoint, so this is a kind of free field that exists on some set x. If you want to map this to any other field L, it's supposed to be a natural bijection sets this set to the getting this field, or forgetting that this field, use this as a set. So it means that the map will be from this set to the U, the other direction.
Maybe just misnotations, because their f was not the function but the object in the field, and you have it as a function.
Maybe.
Yeah, so it was right, but like, yeah, this is also.
I wanted to claim. You say that there is such.
So I think what
I
you're
think
saying
that-
that there is a confusion in the notation. So it looks like you took maybe field L, and then this is what you want, right? But still the map is in the wrong direction.
No.
Yes.
The maps
Because
you
in order
in the
to
right direction.
in order to construct the adjoint functor, you have to move the
This is
arrow.
in the right direction. So the map is from the sum set X to the U of L, where L is equal to, and this is a map in the other direction.
I want to say that here we have usually many elements, there are many maps, but if these have different characteristics, then we have only one map. Yes.
If you have zero maps, if you have zero maps, yes, there is only one zero.
Yes. So if f of x is a set, if f of x is, has some characteristic, we just take L to have another characteristic, and for example, that L has infinity elements, and we can't have projection because
Why?
because cardinalities are.
Well, essentially, so suppose that there is such a function, this one, right? Of course. So if you suppose this is a field. So this field has some characteristics. So characteristic of the f of x, well, is something. So what if I take some L such that characteristic of L is different? I can definitely do this.
Of course you can.
Then, in this case, this will be 0, and this is potentially it's not 0 because it's just a map of sets. Oh, this is just cardinality of this set, cardinality of this set, we need to multiply them. Well, not even multiply them.
Yeah, well, you want to take x that is not zeros empty set.
Oh, if you have a functor, we're supposed to use this on any object.
Yeah, so we just take good. It consists at least like 2 elements.
Yeah,
And that's
for example.
fine.
Okay. is Lipschitz maps.
Oh, can you remind?
Again, forget for function, the question is the same, you have a left and choose. So Lipschitz maps means the following. If you have two metric spaces, this is a map. Say two metric spaces, that the map is Lipschitz, you have the following. The distance of the images
Of X.
x1, x2 is bounded by the distance points up to some positive constant.
So it just bounded by the metric space. Makes sense. Well, we have, like if it was normal space, then it would be just bounded linear operator. So
Yeah. Well, all spaces it's around the edge of space. Also notice that in the fields there are no initial terminal objects. In the fields there are no initial terminal objects.
you don't know what.
And that's a different question.
How does it help us in this particular problem?
It doesn't at all. I'm just saying that the category fields is a general category. No initial objects, no terminal objects, no construction of a primitive field. And in fact, you're going to see there's no products, no co-products. It's a counterexample to everything.
But does it dissolve maybe in some sense into a union of categories of fields of some particular characteristic which harmonize?
Yeah, because if you take category fields, then you can kind of say that this is disjoint union of several categories for each characteristic, 0 at any prime number, and in each of these components there's an initial object, the prime field. There's a characteristic 0 and the prime number. So in all subcategories you have initial objects.
extent is it essential that we consider only the Lipschitz maps?
I don't think this is really important. For example, if you consider older maps, this is still be true. As a metric maps, this is still true for even the simple group. But there's no way to measure those. There's no such thing as a free metric space. So we establish two examples where the answers are negative. There are no joint functions. But if you take, for example, continuous, I'm not so sure.
Because I guess I came up with an example of for continuous maps for some kind of free metric space.
Well, this would probably be just a metric space with discrete metric.
Yes, yes. It seems to work, but not in the Lipschitz manner if we consider continuous maps.
In the Lipschitz case, there is no free metric space.
Well, it sounds natural, but there is no such.
No, the whole category, from the point of view of analysis, the Lipschitz case was the most natural category. The idea is that before you need to, suppose you have this vector F, you compute this on some set X. You want to test it with some other object, and in the previous problem that was object L. So you need to come up with some other object such that it says everything is fine, but for a matrix, something fails.
Essentially, we just need to construct an example where the set of Lipschitz functions are finite or something, and just the function of a set.
I'm not saying that the argument with the regularity would work, but
Like if it's not, so it doesn't, it's not about criticality.
it's about distance.
Yes. Okay, do we need to check some neutrality conditions to see it work?
No, I don't think the neutrality conditions were taken at all in this problem. However, there was no neutrality conditions in problem 1. This is managed to show that there
Yeah,
was.
but we just knew that there are not so many maps between fields with different characteristics, and
No, what you're saying is that you know something about field theory, but you
Yeah.
don't know much about metric spaces.
well, maybe a little less.
Of course, the reason I'm giving you these two problems not because this is interesting categories, but because it's examples where you don't have to left adjoint. So you don't want to automatically assume that you always have a left adjoint. It's very special cases. really don't want to spend too much time on this problem. It's not very clear problem. Let me just choose to call it space. Call this space Z D. As I said, it consists of 2 points, and the distance between these 2 points is D. So then, if you have a free metric space on the X, you look at the maps to this space, and this is the same as the maps in the sets X. Well, here you're just right by the junction. So now we just choose any map here such that it has 2 different points mapping, well, one into A, the other to B. So we choose map F here such that f of some point x1 is equal to A, f of some other point x2 is equal to B. In a sense, it's not very hard to do this. But then, if there is a Lipschitz map here, it means that D is greater, is bounded by C, and then I have the distance on the of x. x1, x2, right?
What is x1, x2 here?
2 points.
And so it shows that f of x is discrete.
No, it just means that there is a point. I mean, it's just by definition of a Lipschitz map. So I choose any map that satisfies this property.
It's just a bit confusing because is there x1 as well in like sets, or is that x comma?
This is x. X called set x. So the set is to the x.
Yeah.
Okay.
So I choose a map with this property. I assume that there is a corresponding Lipschitz map from the f of x to the ZD. If there is one, it satisfies this. Satisfies this condition, right? By the definition of Lipschitz. Well, this is true for any real number D. So this is for any D.
But I think C
But C may
depends
depend
on
on
Z.
Yeah.
C may depend on Z.
This is true for every x1 and x2, and so it shows that f of x is discrete.
Because like for different spaces, C is like different values, right?
So C isn't a constant in our context. It's a function of D.
Yeah, it's a function, of course, of what?
Well, it's a function of the space we're working in.
Yeah, you're right. So there's a dependence on D, definitely.
I think I have an argument, but it might be wrong also.
Yeah, it looks like what they have is not really working in this category, but definitely works, for example, in the small category with contractions.
We should fix C.
No, for contraction maps you use C, and C is just 1.
And in this case,
No, in this case it looks like we need something more, right? I wanted to say that if this is our test space, then the distance between the points is infinite.
I have an idea about this, but I'm not sure. So let's take some finite x, like finite set, and let's see where f of x goes. So I claim that if f of x is somehow infinite metric space, then there will be the difference in cardinalities. If, for example, we take Y to be some finite set, let's say just 1 point. Yeah, and then if x is finite, if f of x is finite as well, so we see that f of x is some finite metric space, we can assume the biggest distance, right, between 2 points. If f of x.
Even if you start this finite x, how do you know that f of x is finite?
Again, if it's not finite, it's one situation, and if it's not finite, I claim that we can take as I know L was used for a vector or for fields, but let's say we take some other metric space, and let's take just finite metric space. I claim then that the cardinality of Lipschitz maps between f of x and y will be different to the cardinality of.
No, it's not just small.
It will be bigger because f of x is infinite metric space, and x.
I'm confused now. What case you?
Can I write it? I might be wrong, but that's the way it works. Again, like so. So again, we take some finite set, right? And we have two like ways. Like if we need to understand if f of x is finite and infinite. No, f of x. So this case, okay? So in this case, I want to assume what? I want to assume, I think, this. And this I can choose. This is some metric space, right? And let's say I take just finite metric space. And well, I would assume there will be a lot of maps here, right?
For example, all just maps of.
Yeah, that just point to some element in one. And here, like. Well, no, maybe it's not working how I want to say it, but so I claim that that's like a lot bigger than what? Then I guess sets. Yeah, because like forget full factor. These are finite sets, basically, because if it is finite, this finite, and this is infinite, that's finite. So I'm not sure how to come up with this argument, but I think that there is some problem there.
If it consists of 1 point.
If y consists of 1 point, I don't think it works, but maybe, no, because there is like one morphism. It's the opposite. I want to say that there are like at least 2 points, and that I can make the maps. I mean, I want to say that the distance between them is small, right? And then maybe there are a lot of maps here.
We know that f of x.
Oh, okay. I can just take some points in f of x. That's true. Some like x1, x2. Like, yeah, just 3 points, let's say. And I can consider distances between them, and then I can take 2 points in y, y1 and y2, and say that, well, I still can choose whatever I want as y, right? So I just say that distance between these 2 points is smaller.
Если f от x, например, прямая, то надо сразу любую. Но вроде мы поняли, что f от x дискретно, поэтому вроде. Вот, вроде если вот, как в предыдущем рассматривали, две точки соединенные на отрезке, в смысле расстояние, это вроде дает, что расстояние x1 и x2, оно ограничено снизу.
Как связано f, которая в второй части set, которая с Липшицем отображением? Просто какая-то абстрактная x.
Yeah. Да, f это. Ну, пока это какой-то функция, которую тебе не построить. So, I mean, yeah, I didn't really come up with this argument, but like in this case, it's kind of trivial, like if f of x is finite. Because if f of x is finite, then what? Then we can just assume the maximal. Yeah. So I just want to say that we can do what? We can just take. We can just count all the distances between elements in f of x, right? It's a finite set. We can count all the distances, and take y as a set of 2 elements. The distance between those is bigger than the maximum of these distances. Well, if this is a finite set, then the set of distances is finite, right? So we can take some distance that is bigger than all these distances, right? And just take y as a set of 2 elements, and the distance between them is bigger than the maximum distance. Then what are the Lipschitz maps? Well, they are essentially those that are sending all f of x to this point, right? No?
Because we can choose any C.
Oh,
Any Lipschitz constant. And then we went from metric spaces to other.
wait, but it shouldn't be C x in some sense. Oh, yeah, C is not fixed. Oh, so it's the same problem with C.
So I suggest we just assume that we consider different category of the state. Metric spaces is construction maps, but obviously my argument works, and this is an example where we don't have an active join. And we can think about what happens if we just.
Is it actually true that there is no finite?
Or I have an example for this. We proved that f of x should be finite. And let's take y to be integers with reduced topology. So if C is fixed, and so x maps to some points, distances, maximal distances is bounded. And the cardinality will be
I think you need to write this on the notebook.
Yeah.
so this is assume we prove that this is finite. So f of x is an infinity, and take y to be integers, and Lipschitz condition means that we consider sorry, no.
Okay, I still want to go to the next one. Because the whole point of this problem 1 and 2 is to show you that there are examples without the joint factors and not to do some magic geometry. So
I hope there will be no such problems like this in the quiz. So.
in the quiz, I'll give you problems where I don't have to know that.
Oh, you didn't know.
No, I saw the problem. I come up with this argument, and I decided that it's fine, but I forget that C can depend on D. So I saw this nice problem, but it turns out it's a little bit harder than I expected. Okay.
Is it home exercise?
Yes.
Do I want this to be?
Yeah.
Okay.
I mean, there's a pre-check.
Yeah. If you do this for the Lipschitz category and give me solutions next time, this will be an additional checkpoint for the seminar. Okay. So now I want to take R and S to be rings. And I want to take B, R, S by module. So to indicate what structure I'm using, so let's take this as a by module. So where is the limits?
R on B is left.
Yeah. So as an R module, this is a left module. As an S module, this is a right module.
Okay.
And these two structures commute. So meaning that if you have a product R ds, then this is the same thing. This is exactly the definition of RS by module. And you can equivalently say that this is the same thing as R tensor S O module.
S what?
O. Opposite algebra. Opposite ring.
Okay.
So this is of course opposite. No, this is because of the right action of S is exactly the same thing as left action of S opposite. And the property that this action can use is exactly this action of the tensor product. So So then with this by module, you can introduce two, well, you can define two functors. Well, let's call this F. R modules to the S modules. So what this thing is doing, though, is taking an R module. Well, probably I want the other way around. So this S now wants to be R. So I want to take an S module and take a tensor product with this by module over S. Right? So S is a left S module. So that's left S structure. Take a tensor product over S. So it's this left left module structure and it's this right module structure. So what's left is just the left. So
Is it going to be somehow related to the pullback sheaf in algebraic geometry?
It's a little bit different algebraic geometry, the sheaf of algebras. Of course, it follows from this what should be combine this together to get what was going on in algebraic geometry. But here you can define factor just like this. And you can factor in the other direction from the R modules to the S modules. Well, now we take an R module and send that R module to the home B. So this is home over R. Now I use R structure on B to compute this home, and what's left is the right S module structure, but home is contravariant in the first argument, so this is a left S module structure.
I'm sorry, it's M for tensor B or B tensor M?
B tensor M tensor B doesn't make any sense. So B is a right S module and M is a left S module, so hence we have tensor product.
What's behind home R?
You look at these things as just hints that allow you to understand what's written here. To take a tensor product, we need the right module structure, left module structure.
No, I mean.
And here, to compute home, we need left module structure, left module
Oh, so
structure.
that's just left modules, right?
Yeah, so I'm considering B as a left module.
Okay.
So I use this structure to compute the home. A priori, this is just an abelian loop, but since I have a S module structure, structure of the right module over S for B, this home is a left S module. Since this is contravariant in the first argument.
And we need to check if they're joint.
So maybe we can skip the neutrality conditions, but compute explicitly a unit in that we will have. Just important to understand that there is no such thing as a tensor product of left and left module, or right and right module. It's not possible to define. For a tensor product, you need one module to be right module, and another module needs to be the left module. That is a product, which is just negative. And here we use additional structure, right? So if I don't have R module structure, this would be an abelian loop, but since I cannot spoil R on the left, I actually have one module. So this is the point why I want to buy module, not just any module. So that's the product saying you consider category of left modules, fix a right module, and that's the product with this right module with the function of abelian loops.
And we should construct natural projection.
Yeah, naturally.
So that would be units.
Yeah, I was asking to construct 5 on the definition of adjoint counters, and then also skip the part that this is natural. So let's believe this is natural. Actually, when you see pi, it's more or less clear this is natural. But I want explicitly you to compute the unit and co-unit.
Yes, I figured that out.
Okay. And the unit co-unit comes now.
Yeah, so these are what I have given out. So can I wipe it out? So what we have to do here is to find some natural maps which will turn out to be unit and co-unit. And they have to be really natural, and I guess I have found them. So what we have here, just for the sake of clarity of the notions, let's say that they are already defined. So what do we have here? F is, in some sense, well, I won't rewrite it once again. My claim is the co-unit epsilon from Fg to this. So this is we have from G to R1. It is what do we need? Fix some m, which is an R module, and we have to establish some kind of connection with f g of n, which is this scary monster. S R n. But the point is, there is some natural map to n, which will be epsilon n. What is it?
Well, you're using my convention with this indices a little bit in a weird scenario. We don't want to write S here, right? Because essentially what you have is S module structure here. So I would put it back to the line module if you want to write this, but not here.
Okay.
But I also don't need to write this. It's just to explain what's going on. If you understand what's going on, you don't need this.
But they are nice as reminders because it's easy to get confused. But anyway, what do we need? We need to take an element from here and map it to somewhere here. But what is it? what is an element of it? It's a tensor product, so we don't know for sure, but we can consider the basic kind of elements which are decomposable tensors. So what is a decomposable tensor in our case? It's some B, which lays at B, obviously, tensor, and here we have some morphism. What kind of morphism is it? It is a morphism F, which is R linear from B to M. So what we have here is, but we can just forget what this sign means. It's just a strange way to put comma here. We have a pair B and a map from B capital to M. So let's please try to define our epsilon to be sending B to f of B. Not B itself, to send all this scary thing to f of B. But at least it's really natural, because what we do is basically take the right hand side and apply it to the left hand side, and we can expand it to the whole module, since these decomposable guys generate the whole module. Okay, so at least one half of what we have to do is done, except for some checks which also have to be done. But let's go on and B tensor some map, some R linear morphism from B to R to N. Yeah, but B tensor F. So here this F is. Okay, that's the co-unit. What about the unit? Unit is constructed in some similar way. We can put this way.
I'm sorry, but don't we have to like check something?
Yeah, we have to, but let's introduce first the unit, and maybe the complexity of what we are talking about will make us forget about the initial intention to check anything, and we'll just get satisfied with the fact that we have gotten through all this mess.
Okay.
What about unit? Unit is eta, and what should it map from to what? Is from 1C modules to GF. Okay, it's as easy as it was here. We have some scary stuff, and we induce something simple from it. Okay, what is GF of M for M R module? Well, it's by definition, as I'll keep using this notation in maybe another way, but anyway, home are B, and now here's the tensor product, B as tensor as M. Oh, it definitely is scary, but what can we get from it? We have to come up with some idea how to map M here. Well, we have to take some M element of this module and map it to some morphism from where to where. Some morphism F from B to B tensor M. Well, here's some heuristic how we do it. We have to find a way to map B somewhere. Where can we map B? Here. Well, we have B as a we have B on the left hand side, and let it stay the way it was. B maps to B. But what to put here? And actually, this M sounds like a really natural way, natural option. So my claim is that this is the unit we were seeking. Yeah, so to sum up, we...
Can we at least check that it's actually a homomorphism of F?
Yeah, I guess we'll have to. But anyway, let's formulate the final statement here. We map M to the map which sends B to B tensor M. So yeah, we have skipped a lot of different checks, which are definitely which we definitely need to do. But at least we have gotten through all this scary adjunction. So we have some monstrous pieces of text, and we managed to figure out what is natural here. So here was the correspondence between B and its image under the map, and here is correspondence between M and the map which sends B to B tensor M. So that's it for what we...
It also looks like a guess at this point, right? So it's very natural guess, but still guess.
Yeah, okay, so now what we have constructed something, we have to check if this works. So there are different levels of check which we can conduct. We can check if these are actually morphisms in the categories which are appropriate. And I guess due to naturality, we can skip this moment because that's not category theoretical questions. These are questions of module theory, at least if you agree. But this is actually a map, and this is actually a map. So yeah, we can speculate about it, but I think that it takes a lot more time than it has to. So let's just check.
What do you want to skip again?
I want to skip the check of the fact that this correspondence, which sends B tensor F to the image of B under F, that's actually a well-defined map from this module, which doesn't, which is not made up of these elements only. It's generated by them.
The fact that this is a well-defined map is clear.
Yeah, but it's clear not from the category theoretical perspective, but from the commutative algebra perspective, which I don't want to discuss right now, as well as I don't want to discuss why this is a well-defined map. So that's what I propose to skip.
Okay, I mean, I'm fine. It's a well-defined map, and I think it's
Okay.
obvious. But like, shouldn't we also check that it's not only a map, but it's a homomorphism?
No. Yeah. What is my proposition is we skip not only the check that it's a map of sets. Obviously, when I say map, I don't say map of sets. I mean homomorphism. But I think that's a trivial commutative algebra check, which we can skip because what we have to really check.
This is not a commutative algebra. This is any algebra.
Well, any algebra. We have to check that these are actually unit and co-unit, and that's, I guess, more essential, at least in the course of class. So let's just ignore some algebraic issues and go straight forward to the issues of category theory. And I guess it's still worth staying on the board, so I have to go somewhere. I don't know where. Maybe.
No, I think you need to raise this. Well,
at least this thing on the top. Raise it. So let's.
maybe
You will not forget how F and G works, right? So
let's keep this as a simple formula. I have O over R. That's the product is what is M, right? We take it as a product over S, moment into F, and this is supposed to be naturally isomorphic to the M over S. Or I guess I'm switching when I work with modules separate for form notation.
Okay.
So So here I have M, and here
They are both in the category, right?
yeah, in the category of modules, R modules, S modules, and here we have B and M. So actually this is the adjunction, and I think it contains all the information. So this is bound to F, and this is bound to B.
Yeah, so we can make some hand waving, some hand waving, and say that is it clear that these two entities are essentially the same? So are the maps from this tensor product to M the same as the maps from M to this thing? I'm not actually sure if it is that clear, not from the perspective of these two maps. So these two maps actually shed some light on the underlying structure of this statement.
Well,
But I guess we can use the best friend of any lecturer and say that that is an easy exercise for the listener.
And it's obvious.
And it's obvious.
I think it's not so hard to actually just construct this map now.
Yeah, but we have actually done.
for me, too, it's also more natural to start with this
Yeah.
and understand the maps in one direction, another direction, then just derive formulas for the unit.
I think it's almost the same that's already been done, but in a slightly different.
Yeah, it's the same information. Yeah. But I just want to say this is quite natural. So suppose you have here some map F, right? So this is what it is. It's just a function of two arguments that takes values in N. And as we want to construct a function of one argument, so this goes to the function of one argument. So N to M belongs to the M, right? So where you could possibly send this F, I think there is only one option that you can write something like this. So that's now this is so we have a function of the B and M. M is fixed. Now you take B. No.
You can take
B is kind of an argument that has a product with M, and then our function F. Right? I think this makes sense.
Yeah, it does.
But
Well, if a function of two arguments, you fix the first argument, and you just compute this as a function that fixed argument as a function of the second argument.
okay, yeah,
Yeah.
it's cool.
Yeah, it is.
So it is not really something complicated and scary. So actually the statement that when you have a function of two arguments, we can introduce partial functions of one argument.
Yeah.
So
In some sense, it's pretty much the point I was trying to make about the terror which is induced by the initial way of writing it and the essence of the link.
And we still have, we need to define map in other direction. So suppose here a function g, what I can write this. So this is a function of if I take g, right? So now I want to
Apply to
I want to understand what it's doing with, say, with a simple tensor, b tensor m, right? So it's sending it. Now if I take this g and compute this on m, I'll get a function, so I'll get a common from this form.
I will apply it to B.
So
Yes.
that's the map in the other direction.
So that's a way of writing this, not in a messy way.
Oh, this is called example kind of very natural candidates for the phi and phi inverse. And you can use these formulas to check that everything is natural. And then you can just use these formulas to derive formulas for the epsilon and eta that you just gave us as a definition.
Yeah.
Now this is one important formula. It means that the tensor product of the bimodule is left adjoint always to the home function with the bimodule. And later we'll see that because this tensor product of home are adjoint functors, we get some kind of theorems for those functors for free. For example, we're going to see that the tensor product is left exact and home is the right exact. So the other way around. So home is the left exact and the tensor product is the right exact, just because they are adjoint functors.
wait, I I agree that it's very natural, but still, is there like an easy way to see that they're actually inverse? Or?
The inverse picture is very easy to get. Yeah, you just point one from another.
Oh, well, yeah, I'm trying, and like, I don't really see.
Well, that's a point represents is the fact. Well, I just want to say that this formula has plenty of variations. For example, the easiest version of this formula is just for sets. Now we can use, say, in this sets, we have two sets, maybe x, y, and z. Take a product of the two sets, add them to the z. This is the same in the sets x, sets y, and z. The same formulas.
Is it a cross? Well, what is the cross product?
It's a product in the category.
Yeah.
Pairs, ordered pairs. So for sets, we have analogous formula. Well, formulas are more or less the same.
So its morphism from product to z is the same as yeah, okay, it's the same.
And for cats, we also have a version of this. So we have cats for two categories, say A and B. Take a product of two categories and functors to the third category C.
What's cats again?
Small category.
It's like that, but with some differences.
Yeah.
So A, B, and C are categories, and these are factors. So here we have y factors, historically C and B, taking values in C. And here we have functor such that for any object of A, we have functor B to C. And here I would say everything is more or less trivial. Here you actually need to check something. It's not a completely trivial observation.
Small categories.
Yeah, objects are small categories, and what is our factors?
And small categories is that everything is a set.
Yeah, I just want to emphasize maybe if you want to solve some problem at home, this might be a good problem, because it looks like we have almost the same information as for set, but in the proof there are some details that we need to check.
But we have after the sets, cats, and categories objects which are cats, etc.
So we have a.
I think one.
Oh, here we don't treat this as a two categories, so I'm claiming it on it just bijectional sets. But you can upgrade this and say that this is actually an equivalence of categories, where these categories are fixed, objects are factors, and the maps, the natural transformations are maps to categories. Okay, these are two remarks. But I want to return to this problem and consider the following situation. Suppose I have a map of waves. So then I have an obvious functor, I have upper star, and the S modules to the R modules. I take an S module, and while this map, this is definitely an R module. Just forgetting this much. Restriction of scalars. Find left and right attributes.
We have to find any, or we have to find any and prove that there are no other.
Well, left and right attributes are unique.
No, what I mean is we have two question marks here.
So for left and for right attribute, In this case, they both exist.
Okay.
I just want to understand the explicit description for those two functors.
And the point is that the functor is contravariant.
Why this is contravariant? It is covariant. It's covariant.
It must be, yes, because it's not a whole, it's a whole.
Of course, you're not supposed to start from the scratch. You need to use previous problem. Somehow everything is about consequences.
Have links with coordinates.
Yes, as usual.
I'm not sure, but it's left joint, maybe it's also right joint.
Probably one.
Can be
So what's the function?
answer. It takes n to n.
But it's only one.
Yep.
Maybe you can explain this.
I found two. Both. But maybe we can discuss.
You both have already managed to get that point to the signature.
Also found out that I haven't yet established the projection.
Well, I don't really think that you need to establish projection separately. You just need to use previous program.
In that case, I can do it.
Oh, okay. Yes. We have such function which takes argument m to n tangent s over r. This is S module, and I claim that by previous exercise there is a natural projection between this homomorphisms and morphisms from n to Rn.
How do you multiply S on the right side? I think we need to watch
I need to see.
left. Because M is left, right, M module, right? And S can be both actually.
You mean here?
Yeah.
My previous exercise, this is motions.
But S is also on the left module. No, it's right.
And from M to
I multiply, but on the right by echo.
from S to N. And I claim that this is essentially S times N.
It would be easier to understand that you write the form over what.
I mean morphisms.
Yeah, but with this formula, always writing home over R or S. So this is helpful.
So this is over S. This is over S. This is over R. This is over R. Yes. this should be also over R. Here we have R, here we should, yes, M is also.
I think this is still not completely correct. Probably this is also S.
This is S.
Why is it that there is a motion?
So F star.
Okay, I understand.
Give me a second. So it takes R module and make it S module and that S.
You can do this in 2 steps. What's home over S from S to N as an abelian group?
What are we trying to prove?
I think we tried to well, this, I don't want to suppose from the previous problem, right? We just want to
I
show.
honestly don't really see it because we
No, up to some change of indentation.
switch a lot of things there
We
and
need to switch RS.
yeah, but like why is there S not like R? Because like
S now is playing the role of the bimodule.
S is playing the role of primary. Yeah, I agree with that, but we have there isomorphism of we
No, you just plug in E is
Yeah,
equal to S
okay.
and then switch around
Yeah,
RS
yeah,
and then you get that formula.
Yeah, okay.
So I think what we're trying to understand is why the right adjoint from
Ah,
principal
okay, now I
form
get-
is this thing, right?
Yes, this map is defined by the image of 1.
Yes. So as an abelian group, this is definitely N.
Yes, and it is a smooth.
So you just use this module structure. You don't understand as an R module why this is the same thing as this one.
So we're checking the upper projection. Okay. Yeah. Makes sense.
I guess it's
Well, there is a notation for this. This is called the induction factor project. And this is also called F flow shrink. And reality what? Low shrink.
Lower shrink.
Shrink. What it is?
Креветка.
No, this is
Какая-то сжатая.
and this is the co-induction method, and this is also notation F low star. So I guess we proved well, that F low star of module M is this thing, right? And this follows by the derivation that the upper star of N is the same thing as the home over S, S, and N. So that looks like the observation.
Yeah, like, and what is the argument again there?
Well, if you just look, won't understand what this thing is, for example, as an abelian loop. Since this is over S, everything is determined by the way you send 1.
Yeah.
Right? Because any element looks like S times 1. If you know the image of 1, you know the image of any element.
Sure.
So, and 1 can go to any element in M. So, this is definitely N as an abelian group. Now, we use S module structure and this S module structure to compute this home, but what's left is an R module structure here. Right, and since this is on the right, we can, and home is contravariant, you get the left R module. And this multiplication of with the elements from the R is exactly the same as we're getting by just forgetting the scalars.
So and this was left adjoint. Well, the right adjoint should be then with homes like this. But
Yeah, that's
like
correct.
home R, taking S as a left module to M. Right. Yeah.
Okay, so M is what? Where is M? This is R module, right?
Yes.
So over R.
S, M.
And this is the co-induction.
And the similar argument here.
Yeah, and again, this follows, since we can reinterpret F upper star of M. So in the previous formula, we interpret this as a home, but we can also write this as a product.
S with R over
Well, what's M? N? N is an R module.
S.
Wait.
Well,
Well, this is a joint, so it goes with this, the other direction. So it's an R module.
M was an S module then or what?
Wait.
I mean, F, M and N should be the modules of a different ring, right? So, but M was definitely a R module, from what I see. At least we assumed homes as R modules.
Ah, sorry, yeah. So now I'm trying to define it again. Just the restriction of scalars. Yeah, for the restriction of scalars, I started an S module, and yeah, I'm sure. M is an S module, and I take this tensor product. So this is as this structure.
This is R module.
Now I'm on the S structure with the S module on the right and this R module on the left. So these two structures are used to compute the tensor product, but I still have this R module structure. And of course, as an abelian group again, since this is just all tensors look like this. Well, only S tensor N. So I can always say that this is one Sn. So there's a canonical map from this thing to the N, which is this one.
Yes.
Okay. And in general, in ring theory, these are called inductions and co-inductions. For example, what you already know. Oh, you probably seen this in the representations of finite groups.
What did you say?
Well, the induction function. So there is a situation where you take H to be a finite side subgroup of G, and there is corresponding map of algebras like this, right? So then, of course, any representation of G is restricted to the representation of H. And then any representation of a subgroup you can induce from this representation of H. And this is done by this function. Let me just have that right. Forget what function. No, there's one subtle point here you can think about this. In this case, induction or induction inside. It's a very special case.
Isn't it a problem or something that the upper star and the lower star F are not induction and co-induction? Induction and co-induction are denoted in completely different ways. But we have two dual notions, induction and co-induction. And independently of that, we have F upper star and F lower star, which is dual notion. So we have dual notions and dual ways of writing something. Why isn't induction F upper star? These are two dual notions, but
Why you want the for induction use notation F?
yeah, well, we have two dual notions. Why don't we have two dual ways of denoting them?
Well,
Because we do all other stuff, but that's not we do all the co-induction. That's something else.
Well, all motions are inductions and co-inductions.
Yeah. So if we do ways of ладно, все это важно. Я ничего уже не сделал.
Yeah, I just want to mention that the adjunction between the induction and the restriction of scalars in the representation of finite groups, this is called Frobenius Pavlov. It was discovered many years before the category theory. And the fact that for finite representation of finite groups, inductions and co-inductions coincide just means that if you switch order in the Frobenius formula, you still get the correct formula. So you can try to do this. So somehow we just need to find the natural isomorphism of the functions, these two functions, in this special case. For finite groups. Then the groups of finite is very important. Okay, so I think that's it for today. Thank you very much.